So in the last session, we have discussed on finite state mission, right? Did you all gone through the examples? I told you just revise interview questions on FSM in digital logic design PPT and assignment, right? Have you gone through that? Have you gone through these examples? Did you all understood? I think everyone got clarity from these examples. If you practice properly, you will get more clarity, the difference between overlapping, non-overlapping. Any doubts from this topic? If you have no doubts, we can continue with programming.
When we use overlapping and when we use non-overlapping?
It totally depends whenever you want to start from. Suppose 1011 is there, 1011. If you want to start after last one, if you want to start again from initial state, then non-overlapping. If you want to start from middle of the sequence, then overlap. Suppose in sometimes if you want to reduce the number of states again without starting from the initial state, if you want to start from the middle of the program, then we can use overlapping concept to save the time. Okay, I think here we have examples for overlapping and non-overlapping also. Difference between Mealy and Moore. Seventh one, detecting the sequence 1010 for serially coming data. How it is detecting the sequence. First at stage A, number 1 is detected and one detected state, then 10101, last 0 will be detected at D, but it is a melee, right? Only 4 number of states will be there. Whatever the sequence number of states we are considering, number of bits, same number of states will be considered. But in Moore, plus 1 state, extra 1 state. Here non-overlapping case, same question 7, but non-overlapping case. Overlapping means what here? 1 0 1 0. Here 1 0 1 0. At this point of time, 0 we got the output. If 0 is detected, output is getting same here. Overlapping is happened because 1 0 1 0. If you put this 1 here, from this one also we can detect the sequences 1 0 1 0. That is overlapping case, so that we can speed up the process. No need to go for initial state again. Okay, if you have more 6 number of states, 7 number of states, even there also we can overlap to make the process speed. Okay, so without going to the initial state, we just overlapping same bit at B. If you want to go for non-overlapping sequence here, 1 0, this 0 is taken here. See, 0 output here, so that non-overlapping case. Okay, 1 0 1 0. Again, it will start from the first cycle, initial state. And also, there are a lot of examples here. And starting from state A, 11th one. Okay, these all are continuation of 111 sequence. Reduce the following state table. Just from directly from the state table, we need to reduce the state. Starting from state A, write the next sequence and output values of the input sequence. Original statement. Input sequence 0 1 0 1 0 1 0 1 0 1. Then what is the next state? So how you will get this next state? Yesterday we have seen one diagram, state table diagram. from that state table diagram, if you write exactly, you will get these many state. And what is the output? The outputs are 0 for all, because here it is just telling write the next state and the output value for the sequence. Here it didn't indicate any sequence, which sequence it is detecting. So output sequence is 0 for here. And state mission to detect these patterns 011 101 110 111. So to detect these, we need to draw the diagram 011 111 010 001. And there are a lot of models for these 4 samples, detecting 4 samples with overlapping method. Mostly these all are Mealy missions only. Today we'll see how to write the program for Mealy and Moore also. This one Moore mission. State question. Draw a state diagram for a circuit. Output is 1 if the aggregate serial binary input is divisible by 5. For instance, if the input stream is 101, output 1, since 101 is a 5. Okay, so 101 is a 5, so we'll get output at that value because it's divisible by 5. Like that 10 is there. 10 means 1010. So it is divisible by 5. And then next 20. What will be the value? 1. Remaining, suppose 19, 18, 17, output will be 0. If it is 25, output will be 1. If it is 21, 22, 23 or 24, output will be 0. So these are the input sequence value output. Input is 1, 0, 1, 0, 1, suppose. Then how to write the sequence? State 1, transmitting 1 and detecting 1, 0 sequence, and then detecting 1, 0, 1, and then 1, 0, 1, 0, and then 1, 0, 1, 0, 1. Like that, how the states will be detected. And the values according to this. If it is a 1, it is not divisible by 5. So output will be 0. For 2 also, it is not divisible by 5. So output is 0. Next to 1, 0, 1, it is divisible by 5. So output will be 1. 1, 0, 1, 0 also divisible by 5. So output is 1. 1, 0, 1, 0, 1. It is not divisible by 5. So output is 0. Like that, whatever the sequence you are taking, where do we get the 5 multiples of 5? There we will write the output as a 0 or 1. So this is what the state table. Any doubts from these examples? Have you tried anyone? Total how many questions? 24, starting from 7. Manoj Kumar, Roshini, Rakshita, Gnan Sagar.
Yes, I have tried some of the questions.
Okay. So do you know how to write the program in Verilog, anyone?
Yeah.
Okay. Have you tried the program how to write in Verilog?
Yes, I have tried.
Okay. What about Sunny and Vinita?
No, sorry, Prasanti. I haven't tried for FSM yet.
Okay, fine. So we will try some of these examples, and also yesterday we have seen traffic light example and some sequence detectors, right? So we will practice few examples today, and next session also we will discuss mostly on some complex examples like ATM mission or vending mission, elevator. These type of examples we can discuss in the next session. Okay, so mostly Wednesday. By Saturday, we will close Verilog. For memories, it will take only one session for theory and a Verilog implementation, RAM, ROM, FIFO memory. 3 memories we can implement. Okay, so by Saturday, we are going to complete. Okay, but I don't know whether you are completing the assignments or not. I'm receiving only from few students. Did anyone tried the counters examples in Verilog? Counters examples.
The questions, I mean.
Shared in mail? Okay. Okay, so theory wise, you already know what is meant by finite state mission and what is the difference between Mealy and Moore mission and how to draw the circuit diagram, right? So we will write the program for a few of the examples today. Yesterday I already explained this example, right? To detect the sequence number of consecutive ones. Consecutive ones means a repeated number of ones, three or more number of times. If three times detected, then we'll get the output 1. If 4 times detected, we'll get the output 1. So whenever more than 3 ones are repeated, we'll get the output as a 1. So for that, we have written the state table and also state diagram. Okay. Next, coming to the example, next example, Mealy and Moore FSM types. Example 1, there are 3 lamps, red, green, yellow, that should glow cyclically with a fixed time interval, suppose 1 second. For 1 second, every color is going to glow. Okay. So what are the observations? The FSM will have 3 states. Okay, corresponding to glow the state of the lamps. The input is set null. State transition will occur whenever clock signal comes. Okay, this is a Moore mission. Moore mission means what? The output will be dependent only on the current state. So since the lamp that will glow only depends on the state, not on the inputs. Okay. So this is what the simple block diagram. Clock is a input, red, green, yellow are outputs. So here it's a very simple design, but in future if you want to design with the more features, like how can we design with the more features? We can include some more delay, or we can include the dependency signal. Suppose one red color is high, means remaining 2 sides will be red, yellow or green. And if one side is yellow, remaining 2 sides will be red and green at a time. Parallelly, we need to write the three conditions, but here we are writing only single condition. Okay, so after this example, try with 3 conditions parallelly, so you will get more clarity. Okay, so first, how to write the program. Verilog program is very simple in whatever we are writing in finite state mission. Normally, for combinational or sequential logic circuits, registers, counters, we have different modeling styles. We will write in behavioral modeling, data flow modeling, gate level modeling, structural modeling, and CMOS level, switch level modeling. But if for finite state mission, we follow only one method. Okay, in that also, what are the optimized ways we will follow? That is a behavioral modeling only. Mostly we will write in a behavioral modeling. In industry also, I already told you a lot of times. We never use gate level modeling or structural level modeling because those are very complex programming styles. Okay. So if you want to implement a counter logic in structural modeling, we need to include lot of lines and also structured way we need to write connections are very important. Even wire connections also very important. But if you write same program in behavioral modeling, just we need to do the increment operation or decrement. Okay, so that is how we can write very simple logics in a behavioral modeling in just a single line or 2 or 3 lines as a functional device. Okay, so in FSM also mostly we use behavioral modeling only. Okay, so module, name of the module, cyclic lamp and clock light. Clock is the input, light is the output. Light can be either red, green, yellow, any one. So input clock, output reg. Output is declared with the reg data type. Why? Because here we are using the procedural assignment statement called always block. So true down to 0, light, parameter. Whatever the statements we are using in that case, mostly we use the parameter with some variable. Okay, for good programming style. Whenever other, suppose if you are writing your own program, you can understand easily. But whenever others, if anyone view your program, it will be confusion if you put like numbers 00101111 like that. Instead of that, if you put some variable, if you mention in a variable format, that would be very good looking and easy to understand. Okay, so for that purpose here, case state, how many states will be there? 4 states, right? 3 states, but even 3 states also it comes in a 4-bit. So 00, first state, 00 means S0. So S0 is equal to 2-bit binary 00 assigned. Next S1. S1 means 2-bit binary 01. S2, 2-bit binary 10. These are assigned. And parameter, red, green, yellow. Even these are the outputs. So when you will get the output, suppose present state is some green color, then what is the output? Like that output you need to mention. If you mention output as a 0010, same, it will be also not good looking programming style wise. Okay, so that's why we are taking the parameter here. Red is equal to 3-bit binary 100. Green means 010. Yellow means 001. Like that, we need to declare some constant values to these variables. So internally, program within the module, whenever you use those variables, it will be assigned that particular value. Okay. So if you want to use module to module, then how we need to change, like global declaration, what we need to write for global declaration? What we need to write for global declaration? We already discussed. Parameter is a local declaration, right? For globally, what we need to write? Is there any macro or is
Define.
there any parameter? Define. Okay. Have you gone in parameter? We have different types: def param, local param. Have you gone through that? Yesterday, I have shown you the interview questions in Verilog HDL. In that, those things are mentioned. Def param, local param. For freshers, it is not required, but if you want to learn very deep, then you can go through those questions. Okay, anyway, we use define, tick define, which is a macro to declare globally, right? Next, reg state. We need to declare what is the present state, what is the next state, 2-bit size, 1 down to 0, because only 3 states are there, right? So 2-bit. Always at the rate of POSIX clock begin based on the state. Current state is S0. It is in a present state S0. Begin, present state is a red. Okay, then what will be the next state? Next state will be the light. Okay, light is the output here. So green, output is a green. And state means next state here, defining next state. So what is the value of next state? Next state will be the S1. So current state is S0. Next state will be S1. And in current state, what is the output? Current state output is a green, G. I am mentioning as a G. And current state is in S1. Begin. Then what is the output? In current state, we'll get the output as a yellow, Y. And what is the next state? Next state will be S2. S2. And current state is in S2. Then what is the output? Output is yellow. Then what is the next state? Next state will be S0. Okay, this is what the cycle. And by default, why do we need to write the default light equal to red, state equal to S0? What happens if we don't write the default statement in a case?
We will get some latches maybe.
Okay, we'll get the latches. To avoid the bad latches, we need to write the rich, default statement. Okay, so if you write the test bench for same example, module, test bench, cyclic lamp, rich, clock, wire, 2 down to 0, light, and name of the, DUT, generating the clock, initially clock equal to 0, and dollar finish, and dollar dump file, dump files, and monitor. So what is the output? We can check the result. So we'll do the simulation. Any doubts still here?
Could you please
Any
explain
confusion?
why we use a non-blocking assignment here?
Sorry.
Could you please explain why we are using non-blocking assignment here? Like, for example,
For
light is
mostly, why do we use non-blocking assignment? Good question. So you need to tell that anyone can answer why we use a non-blocking assignment here.
Because output, we don't want output to be updated, and it is a Moore machine here, so it just depends on the present. Just depends on the input.
Okay. Any other answers? From others? Even for registers, counters also we use non-blocking only, right? For sequential logic circuit, we use non-blocking assignment.
It's non-blocking.
For combinational logic circuits, we use blocking assignment. So why we need to do that? Why particularly sequential logic circuits are declared with a blocking? You assigned with a non-blocking. Whenever we discussed blocking and non-blocking assignment, I already told you to practice this example. Like suppose if I am assigning, there are multiple number of blocks here. Block 1, block 2, block 3. So the output input is assigning to here and here and here. Output is getting here. So here suppose output is D0. D0 is assigned with the I, and here D1 is assigned with the D0, and last one is a D2. D2 is assigned with the D1. So if you do same thing using blocking assignment and non-blocking assignment, what would be the difference you will observe? I already told to do the synthesis for this example.
In blocking assignment, the right side value will be immediately as the left side value. In non-blocking assignment, it's going to go through like all the variables, and then after the end, it will start assigning the values.
Okay. Okay. Wait. Just wait.
But in
Rakshita,
blocking, it
can you
happens
answer? Just wait,
immediate.
Roshini. Rakshita, can you answer? What is the difference here? If we use blocking and non-blocking, what is the difference between both? We already discussed this example. Vinita, can you answer? Smalata?
And the same thing what Roshini she said, right? And after by adding that timestamps also.
Mm.
Here the outputs are updated, it is just all outputs will be reflected at the end.
All the outputs will be reflected at the end.
I mean to say, like whatever the like whatever you shown, right, in the slide, where
Hmm.
D0 is D1 is updated with D0, like that.
Hmm.
D2 will be updated with D1 because it's a blocking ones.
Hmm. Okay, what will be the circuit diagram for this blocking assignment and non-blocking assignment? Suppose I am taking here I value is equal to 10, D0 is equal to 20, D1 is equal to 30, D2 is equal to 40. So what will be the circuit diagram representation for this blocking and non-blocking? Sunny, can you answer? Tarun, Manoj Kumar. You're already there, Sunny, I think, before whenever we discussed.
In blocking assignment, there is a sequential execution.
Mhm. Non-blocking means, is it not sequential?
No, it will be in concurrently.
Okay. Okay. Still, what are the differences between blocking and non-blocking? Can you tell me what is the answer for D2 here, if it is a blocking or if it is a non-blocking in both of the cases?
In D2 will be, like, for example, D0 is,
20.
it depends on the
20.
value of D0, but in blocking, but
D0.
D2 is not dependent on D0 in non-blocking.
Okay. You're not telling full-fledged.
In the non-blocking, it will be the same thing, what 30.
Okay.
Yes, that is correct.
Okay. So if I consider it as a blocking assignment, what is the value of I? Before that, if you understand, if you remember the rules in blocking assignment, the previous value will be retained to the next value. Whatever the previous value we are storing, it will be retained. Uh, for non-blocking assignment, the value will not be retained for next statement. Okay, whatever the initial value is there, it will be considering that initial value only. In blocking assignment, all the statements will execute serially. In non-blocking assignment also, all statements will execute serially, sequentially, one by one, because both of the statements we are writing within the begin and block. Begin and block is a serial execution statements. Fork join is a parallel execution. Okay, but in blocking assignment, we use a regular delays, LHS side, but in non-blocking, we use RHS side. Here you need to understand inter-assignment delay and intra-assignment delay. We already discussed these delays also, intra and inter. I have shown what is the difference between these two delays. Okay, so when the value is executing and when the value is updating, that is only difference we need to observe. Okay, so in non-blocking assignment, we use a RHS side delays. Okay, because of that, it will look like a concurrent execution, but both will execute sequentially. Okay, because of the delays, the delay will be executed at particular time and assigned at whatever the delay we mentioned at right hand side, at particular at that time it will be assigning the value. Because of that, it will be look like concurrent execution. Okay, but both of the statements execute sequentially. Okay, and coming to the values here, uh, as a blocking assignment, it stores previous value, it returns the value to the next statement. So here I is equal to 10, so 10 is assigned to D naught, so D naught is returning its value, and here also same value it will be reflected. So 10 here also 10 is getting, and D1 also 10 here, and this 10 is getting here. So D2 finally we get 10. That means what? Whatever the input I is there, that I is directly assigning to D2. Here it is not doing any shift operation. Okay, but Same case, if you consider as a non-blocking statement here, suppose I is equal to 10. Okay, so D naught is assigned with the 10. Okay, and here D naught will return it. It will not return its a previous value. It whatever the initial value is there, it will be considered that value only in non-blocking assignment. So what is the value initialized with the D naught? 20. So this 20 will be assigned to D1 here. Okay, and what is the initial value for D1 here? 30. So this 30 will be assigned to D2 here. So if you draw the circuit diagram now, first this I is assigning the value here. Whatever the I value is there, that I value is getting assigned to D naught, and next flip flop, what value is getting assigned to D1? D naught value is getting assigned for D1. So here D1 is getting this D naught value, and next flip flop, what value is getting for D2? D2 is getting D1 value. So here for D2, it is getting D1 value. So if you observe particularly here, shifting operation is happening. Okay, so that's why non-blocking assignments are used for particularly for sequential logic circuits like registers, counters, finite state machines, for all this. Okay, but here it is not doing any shift operation, just value is moving in the same block. Okay, so that's why mostly non-blocking assignments we will consider for combinational logic circuit. Blocking assignments are considered for combinational logic circuit. Non-blocking assignments are considered for sequential logic circuits. Okay, clear everyone? Understood? Clear?
Yes.
Who asked this question?
Yeah, yes, clear.
I am taking same code here also and the test bench. So cyclic lamp, test cyclic lamp, clock. Okay. Waveform, run. Output is again now. Fine. Red means 100, green means 10, yellow means 1. So output red, red is getting first, green, yellow, red, green, yellow, red, green, yellow. So that is what our state diagram, right? So according to the state diagram, red, green, yellow, red, green, yellow. In traffic light controller also same, it will rotate in the same direction, right? Red, green, yellow. But based on the time, if you want to put 30 seconds delay between each color, or 1 minute delay, sometimes 60 seconds also will be there, right? Like that. If you want to add extra signals like crossing signal or any like wait signals, we can add those also. Okay, but this is what simple final state mission for traffic light controller. Everyone understood? And here also you can check what is the output light state: red, green, yellow, red, green, yellow. Each time 5, 15, 10, 25, 35, 45, 10 time units delay. Okay, any doubts? Did you all understood how to write the program? Hello.
Ma'am, can you show me the test bench code for this design?
You can see here. First writing the module, clock, light, DUT, clock generation. Here we are just writing the clock. Automatically the light will be generated here because we don't have any control signals. Okay, this is basic example, but we will see more examples when we took the more number of control signals and sequence detectors. You will get the clarity. This is for Moore mission. Clear? Any doubts? Hello.
Just a small doubt here. How we are calling the, like, we generally use DUT, right? Cyclic lamp DUT.
Between DUT?
In the test bench, we call the DUT, right?
Mm.
It is written lamp over here.
Cyclic lamp. So design name is cyclic lamp. So
Mhm.
here cyclic lamp. This lamp name is just a instance. You can write any name for instance.
And
Sometimes we will put as a DUT,
yeah, yeah.
or sometimes you can put as a lamp or whatever the name. Just we need to put the instance name.
Every time I saw DUT, that's like okay. Okay.
Okay. So next example. Suppose here another style I want to tell. So how we can simplify the same code in a more optimized way, just without writing these many lines. How we can write simply. Suppose if you generate the circuit diagram for this, okay. So how the synthesis? So we'll do the synthesis also. So how the circuit diagram will be generated for this? Okay. So it will generate 5 number of flip-flops. Okay. Why? Because here, if you observe, always at the rate of posage clock. Okay, based on the posage clock, how many values are dependent? So based on this posage clock, one is a light. Light is changing. What is the size of light? 3-bit size. 3-bit size means to store each bit, one flip-flop is required. Okay, so for total 3 number of lights, 3 number of flip-flops are required. Okay, and also we are defining the states here, 1 down to 0, 2 states. For 2 states, 2 bits. 1 down to 0, 2 bit means 2 flip-flops it will be required, right? Both state and output, both are depending on the edge of the clock. Okay, so total 5 number of flip-flops are generating. So without generating 5 number of flip-flops, how can we write this design in a simple way? How can we reduce the number of flip-flops? That's what my question. How can we reduce the number of flip-flops? Any idea?
Can we use indexing here? Is it
Index?
indexing here?
Okay, what indexing you want to use?
I
Like
mean,
how?
state versus this output, right?
Okay. State versus output. Any other answers? Not indexing.
Can we use the shift operator, right? Right shift, 1-bit right shift.
Shift. Okay, 1-bit right shift. So how it will be used?
I mean, 1-bit right shift means that for red, if 1-bit right shift means we can go for the green, and one more right shift means yellow within the 3.
Then for shift operation also it will be generating the number of clock cycles, right?
Yes.
Can we use single bit like without using 0 0 0 1 1 0, not like that. Let's take 0 1 0 1 like that. In that case, flip flops will be reduced, right?
Okay. How many number of flip flops are reduced in that way?
As you said, in output we are taking 3-bit size. If we take 1 bit, then two flip flops would be reduced.
Output you want to take 1 bit.
1-bit size. Like if we take S0 as 1 bit, one flip flop will be reduced. So like that,
Then
reducing
what
of
about S1, S2? If you take 1 bit for S0, okay, second bit will be S1. Then what about third state? We have 3 states, right? 3 statements, obviously 4 cases will get. What we can do means here, if you observe properly, case state we have taken. Okay, state is depending on the positive edge of the clock. Okay, and the light is also depending on the positive edge of the clock. Okay, if you don't write this light here, light is nothing but output. Okay, actually here there is no need of writing the output here because we don't need to depend on the clock here. Light is depending on only state S0. If current state is S0, output will be green. If current state is S1, output will be yellow. If current state is S2, output will be red, right? So here this output is not depending on clock, just depending on state, but still we are writing inside the edge, clock edge only. Okay, so without writing like that, suppose if you write separate always block, one always block is for state, positive edge of the clock, state is changing with respect to the clock. Another always block, if you write always at the rate of state. Okay, so light is dependent on state particularly. So automatically it will generate a combinational logic circuit. It doesn't generate the sequential logic circuit, and it also flip-flops. Okay, so first states it will generate 2 flip-flops. For output it just generate a combinational logic circuit. Okay, did you got my point?
Can you
Can you
explain
repeat
one?
once again?
Yes.
Okay, I'll show you the example. So if you see here the comments on that particular solution, the synthesis tool will generate 5 flip-flops in total. 2 flip-flops for storing the state, 3 flip-flops for storing the output lines light. However, it is unnecessary to store the output lines in a separate flip-flops, as the output values can be directly derived from the state. Okay, so how can we achieve this optimization? Just now whatever I told, that simply in that way we can write. Okay, so separate the assignments to light into its own always block. Use blocking assignments to assign values to light based on the state change, not based on the positive edge of the clock or negative edge of the clock. Okay, rather than triggering the output updates on the clock signal. So here we are not changing the output with respect to the clock signal. We are changing the output with respect to the state. Obviously, state is dependent on clock. So output will be dependent on state. Okay. So by implementing this, the output lines will be combinational and not stored in flip-flops, reducing the hardware required and improving the efficiency. Okay, this is how we can do. And here is the example. So before, same example, always at the rate of passage clock. Inside we have a case state. So if present state is S0, next state will be S1. But parallelly we have written light also. Light equal to green, light equal to yellow, light equal to red, like that. Okay, but here we didn't written light. That means we didn't mention the output here. So output is not depending on the clock. So it doesn't generate any flip-flop because the output is not storing in a flip-flop. Okay. So if you observe right hand side, out always at the rate of state. State means what? It's a combinational logic circuit. Okay. Begin case state. If present state is S0, then output equal to red. If present state is S1, then output equal to yellow. If present state is S2, then output equal to yellow, green, yellow. Okay. So this is how we can reduce number of flip-flops. So totally how many flip-flops will be generated now?
Only 2.
Total how many? 2 number of flip-flops, because only state is depending on the clock edge. State is declared with a 2-bit size. Yellow is dependent on the state, but yellow is a 3-bit size, but still it doesn't generate any flip-flop. So we'll do the simulation and check. Did you all understood?
Still have one question here. Since we mention output as a register, right? There we mention output as a light. So that register will be empty, right? That means we are not using anything, even though we define it.
Here, output rich.
Yes, yes.
It just register means here it just stored in a temporary just output. It doesn't generate any flip-flop here. As we have written in a always block, it just write in a particular register. Register is a temporary storage element, but it doesn't generate the flip-flop in synthesis.
Okay, okay. Thank you.
Particularly in synthesis, if you see behavioral modeling, we never get proper gate level circuit diagram, okay, in proper flip-flops. But in this case it just stored the data, that's it, in test bench wise, but in design wise it doesn't generate any circuit.
Okay.
Same test bench. same output. 1 0 0 1 0 1, red, green, yellow. And here also red, green, yellow, red, green, yellow, red, green, yellow. Okay. For this program, after the session, I will give you the few final state missions. Already there are a lot of assignment statements here. You can try for these, but for especially for traffic light controller, I will give you one problem statement. Okay. You can try that and let me know whether you can able to get the output or not. Okay. So this is one of the problem statement. And also finally, if you take the logic expressions from the state diagram, you will be getting like this. S0 means 0 0, S1 means 0 1, S2 means 1 0. Next 1 1 is a not used. We don't have any state for that. So red means 1 0 0 as per our consideration, how we have written in the program. G means 0 1 0. Yellow means 0 0 1. So based on that, how we are getting the logical expressions we can write. Okay. And next, final state mission for sequence detector. So how we are detecting the sequence here. So what is the problem statement? The circuit accepts a serial bit stream X as input, X as an input, and produces a serial bit string Z as output. X input, Z output. Whenever the bit pattern 0 1 1 0 appears in the input stream, its output Z is equal to 1. Whenever we get 0 1 1 0, whenever the sequence is detected 0 1 1 0, output will be 1. At all other times, whenever it is not detected that particular pattern, at all other times Z is equal to 0. Okay. Overlapping occurrences of the pattern are also detected. Overlapping case. This is a Mealy mission. Mealy mission. Okay. So what is the input sequence? 0 1 0 1 0 1 1 0 1 1 0, like this. Okay. So what is the pattern? 0 1 1 0. Where we are getting 0 1 1 0? Here. This output is reflecting here. As it is a overlapping, here also output is getting 0 1 1 0 here also. Okay. So here you may confuse because the value is not getting properly here. So I have written separately. See, 0 1 0 1 0 1 1 0. So at this point 0 1 1 0, here we got the output as a 1. Again 0 1 1 0. It's a overlapping case here. 0 1 1 0. Here also output 1 is detecting. And 0 1 0 1 1 0. Here also output is 1. It is detecting. And 0 1 1 0. So output will not detect. Okay. So how to write the program to detect this pattern? Okay. And that too, it's a Mealy mission. So this is what the circuit diagram to detect the pattern. Okay, what is the pattern? 0 1 1 0. 0 1 1 0. So initially reset state, here 0 is passing, 1 1 0. 0 means whenever it detects, here we get 1. 1 means we get the output. And we need to write what is the present state, what is the next state table. Okay, write like this. What is the present state? What is the next state? Okay, how you need to write the table? this table based on the 0, 1, 1, 0. Initially state A, B, C, D. Okay. So 4 number of bits means 4 number of states will be there. Okay. So if reset is high, all will go to reset state. For state 0, that means A. Every state have two cases, 0, 1 case, and here also 0, 1 case, and here also 0, 1 case, and here also 0, 1 case. Okay. So you need to understand that I'm telling overall 0, 1, 1, 0 case need to detect. Okay. So here 0 and for B 1 and here 1, 0 and here 0. At this point, we'll get the output as a 1. Okay. So based on that, you need to draw the circuit diagram. Remaining all cases, it will be 0. And also you need to draw what is the present state, what is the next state. If it is a 0, where it will be going. If it is a 1, where it will be going. 0, 1. Like that, you need to draw the state table. Okay. From this also you will get the state table. S0, S1, S2, S3. For S0, 0, 1, 0, 1, 0, 1, 0, 1. So 0 means here. Okay, here 1 by 0, not 0 by 1. It's a 1 by 0. Okay, 1 by 0. So 0 means going to S1 state. S1 state. And 1 means S0. And here 0 means S1. 1 means S2. Here 0 means S1. These things you need to write in program. 1 means S3. Here 0 means S1. Getting the output here. 1 means S0. Okay. The only
Why
this
S1
output
state,
will be
Shanti?
1. What?
Why it is S1 state and at S2 stage, if it is 0 means S1?
Here S1 is storing 1. It is not storing 0. S1 is the S2 is storing 1. S1 is storing 0. That's why this 0 and this 0 we are passing here. If it is storing 0, then you can pass to here.
Okay. Can you repeat once this one?
See here S1 is storing a 1.
Yes.
This 1 value is storing and also passing this 1 value to here. That's why here S1 is particularly storing 0 value. That's why here we are passing this 0 value to here, and from here also this 0 value here. And S3 it is passing 1. Okay, you may get the doubt why it will not put here 1 and why it is putting at initial state. If you want to put here 1, then you can put, but you need to check the sequence whether it can able to detect the sequence or not. Overlapping case also you need to check. Okay, here it will not detect the sequence if you write the 1 here. If you write at ideal state, then only it will detect the sequence. Next sequences also every time you need to check.
Okay.
Okay, so in this particular case only we'll get the output as a 1, remaining all or 0 only. Okay, can you take the screenshot, this one, if you have mobile phone, everyone, so that I no need to change like this whenever I explain the code. I no need to change the screen always. did you all took the screenshot? Okay, see. Now observe the state machine and see here. Module sequence detector, X, clock, reset, Z. These are the port list. X is the input, clock, reset, control signals, Z is the output. Okay. Input X, clock, reset, output Z. Okay. And parameter, 4 number of states are there, right? S0, S1, S2, S3. So S0 means 0, S1 means 1, S2 means 2, S3 means 3, declaring the constant values. And we need to write what is the present state, what is the next state. Okay, present state, next state. In Moore mission, mostly we don't have the present state and both the states. We have only current state, present state, right? Only one state. So in Mealy, we write both present state and the next state. Always at the rate of POSIX clock or POSIX reset. It's a asynchronous signal. Okay, you already know what is the difference between synchronous and asynchronous and how we can differentiate in a Verilog, right? So if reset is high, present state is equal to S0. This line, whatever these two steps are there, these two steps are common for all examples. Any example, whatever the example you have considered, even projects also, this condition is same. Okay, what is the condition? If reset is high means any time the state will be in a ideal only. Ideal state is nothing but S0 state only, right? So if reset is high, present state will be always in the ideal state. That means S0. Okay. Else, if reset is not high, then the state can be any state, whether S0 or S1, S2, S3, it can be any state. So that's why we are writing as a next state. Whatever we mention here as a next state, so it can be any state. Okay. So present state equal to next state. Next, always at the rate of on what signals it is dependent, you can put directly star. If you are in confusion, you can directly put the star. Even the control signals and main input signals will be assigned here, okay, automatically. And case present state, based on the present state, we need to write what is the output and what is the next state here. Okay, so present state and next state, even output also we are writing it same in the same always block. Okay, you may get the doubt, before we didn't write in same always block, but why we are writing now? Because before only state is dependent on the clock. Okay, output we have written in a separate always block to reduce the number of flip-flops. Okay, here the state and this next state, both are depending on this PS and X. Okay, so it's a purely combinational logic circuit, and also the clock will be generated only for the states, present state and next state, not for the output. Okay, so current state is S0, begin. Then what is the output? If present state is S0, what is the output? Go to the circuit diagram and check. Output is 0, right? Even input may be, oh, I deleted. Okay, even input may be 0 or 1. So if you see here, either 0 or 1, the output will be 0 only. Okay, then what is the next state? That will be dependent on either 0 or 1. Okay, if current state is 0, then output will be S0. If it is 1, then S1. Okay, so if you see here, if it is 0, S1. If it is 1, S0. One or 0, right? True conditional, false conditional. 1 or 0. So if x is a 1, next state will be as a 0. If x is a 0, next state will be S1. It's a conditional operator. True conditional, false conditional. Here also same. If present state is a S0, then what is the next state? If it is a 0, then next state will be S1. If it is a 1, next state will be S0. Okay. Next, if current state is S1, then what is the output and what is the next state? Output will be 0 in both of the cases. Whether it is a 1 or 0, output will be 0 only, because here it is not detecting the value sequence. Then what is the next state? If present state is S1, then next state, if it is a 1, then S2. If it is a 0, then S1. Okay. So see, current state is S1. If it is a 1, S2. If it is a 0, S1. Is it correct? And current state is S2. Then what is the output? Here also it is not detecting the output. So both of the cases 0 only. Then what is the next state? If it is a next state, if it is a 1, S3. If it is a 0, S1. So if you see here, current state, if it is 1, S3. If it is 0, S1. Is it correct? And next, S3. S3 is a present state. Now, in which case it will detect the output? Our sequence is 0, 1, 1, 0. Okay. So for 0, 1, 1, 0, it will be detecting the value. So 1, 1 case, 0 case, 0, 1, 0. So here it will be detected 0, here it will be detected 1, here it will be detected 1, here it will be detected 0. So at this particular case, we get as a 1. Suppose if it is detecting as a 0, 111, then when it will detect, in this case it will be detected. Here we'll get 1, here we'll get 0. Okay, but Howard sequence detector is detecting 0, 1, 1, 0. So that's why in false case we'll get as a 1. Okay, then what is the next state? What is the present state? If it is 1 as a 0, if it is 0 as 1. Okay, so current state is S3. If it is a 1, S0. If it is 0, S1. Okay, S0, S1. Clear? Everyone understood how to write the program? Very easy. Like that you can use if else. If else also you can use without conditional operator. Okay, any doubts still here? Shall we do the simulation? Here is the test bench. Module sequence detector. So what is the sequence? The same sequence we can write in test bench. So what is the sequence? X equal to 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 1, 0. This is what the input sequence. Okay. You can also use $random instead of assigning the hard-coded values. And here is the test design program. Okay. We'll do the simulation. And run. Okay. What is the output? Initially reset is high, so output is 0 and input also not considerable. From here, what is the input? At this 0 and 1, 1, 0, 1, 1, 0, 0, 1, 1, 0. What is our sequence detected value? 0, 1, 1, 0. So whenever the 0 is detecting here, output will be high. So in this case, here it is detecting 0, 1, 1, 0. So output is high. And here overlapping case 0, 1, 1, 0. Also output is high. And 0, 1, 1, 0. Output is high. Remaining all cases, output is 0. This is how we will detect the sequence pattern. Clear, everyone? Till here, any doubts? Not clear? Hello.
Show me the test bench now.
See here, test bench. Where you need to understand. What about others? Manoj, Kumar, Roshini, Rakshita.
It's clear, ma'am.
Yes, ma'am, it's clear.
Okay. Next example, we can try for any one example. Describe a finite state machine 111. It's a simple thing. draw the state diagram to output A1 for one cycle. If the sequence 0, 1, 1, 0 shows up and leading zeros can't be used in more than one sequence. So state mission to detect 0, 1, 1, 0. It's also a melee mission. Check for the bit pattern 0, 1, 1, 0. The end 0 can't be used. Can't be used means it's a non-overlapping case. We cannot write overlap. So after detection of one pattern, just go to initial state. This is a non-overlapping case. So here diagram is there directly. We can write the program for this diagram, right? How can we write the program? We'll write differently because it's a normal case. It's a very simple method. You also can write. You can try in this same model. What is the present state? What is the next state using the case? Okay, but we'll try in a different way. So what are the ways we can use? Do you have any idea?
You can use if else.
If else, okay. How can we use if else?
So when we are at state A, if the input is 1, it will be in A, else it goes to B. The next state is B.
Okay. What is the pattern? 0, 0, 1, 1, 0. So initially state A. State A to okay, 1 is reset case, 0 is moving to B, and 1 0. Okay, we'll write the design code. Zero, 1, 1, 0, right? So what are the input and outputs we can consider? Clock, reset, input signal, output signal. Next, before all examples, we have used the parameter, right? So without using parameter, is there any other data type? Is there any other data type? In system Verilog, we have lot of data types like enum data type, type def. Do you know type def? Here we can write S0. S0 means assigning 2-bit binary 00. S1 means 2-bit binary 01. S1 2-bit binary 10. S2. S3 2-bit binary 11. So this is what enum data type. For this enum data type, we need to write the any of the name. Suppose state. State is the name. As we used type def, by using the state, we can create any of the states like state enum. By using this state enum, we can create the present state and next state. State enum, present state, next state. Okay, like this. Before how we used here using the parameter state 0, state 1, state 2, state 3, and here separately reg present state and next state. Like this we have created. Okay. Here we used enum data type and type def ps ns. And how we can write the program? We need to write the reset logic first. So here we have written this reset logic, right? Here also we need to write the reset logic first. Always pause h clock, pause h reset, if reset is high, then present state will go to the state as a 0. Here is 0. Else present state will be the next state. Same logic, right? Here also we have written same logic. End. After that, we need to use the combinational, any inputs. I'm just putting as a star. Okay. Begin. Case based on the present state. What happens if present state is S0, S1, S2, S3. If present state is S0, if input, I'm writing if else. Before I used this statement, right? Conditional operator. Now we can use a if else. Okay. So if input is high, then what is the next state? Go to the diagram and check. If input is high, then next state will be the A. A means what? As a 0. So as a 0. Else next state will be S1. Here for 0 case, next state will be B. That means S1. Next, if input is high, then what is the next state? Check here. If input is high, next state will be C. C means S2. Next 0 means S1. So next state will be S2. Else next state will be S1. And for S2 also. If input is high, then what is the next state? Else what is the next state? If input is high, what is the next state? Else what is the next state? Check here. C1 to DA. D means S3A, and here S1, S0, S0, both S0, S0. Okay. So here S3 and here S1. Here S0 and here S0. Okay. By default, you can put S0. Okay. End case end. So here we have written what is the present state, what is the next state. That's it. But we need to write the output also, right? Here we have written output in the same block. Okay. But here output, if you want to write same in this case, or else you can write separately also. Okay. Suppose output, if I write with respect to the positive edge of the clock, with respect to the clock I am writing, then how we can write? If reset is high, output will go to 0, else if, what are the conditions? 0, 110. So state 3 is 0. If present state is equal to state 3 and input will be 0, right? Last case will be 0. Then out is equal to 1. Else out equal to